will discuss one of the application of pH partition hypothesis. pH partition hypothesis, which is also known as Henderson-Hasselbalch equation. So this is a continuation of general pharmacology topic, that is pH partition hypothesis or Henderson-Hasselbalch equation. So today we'll see how this concept is applied to our local anesthetics. These are not anesthetics. These are local analgesics, because anesthesia itself says there is a triangle of anesthesia, that is loss of consciousness, muscle relaxation, and analgesia, that is loss of pain. So these local analgesic, there is no loss of consciousness, but this part, loss of pain, analgesia, we are able to achieve analgesia. So these are local analgesics, because for anesthetics we need these three properties at least: muscle relaxation, so these are local analgesics. So we'll start our topic with this pH partition or Henderson equation. As you know, most of the drugs are either weak acid or weak base. Most of the drugs are either weak acid or weak base. So what are weak acids? Weak acids are those which can donate proton. Weak bases are those which can accept a proton. Weak bases, for example, local anesthetics. If you look at their structure, this is the aromatic ring, this is intermediate chain, and here we have tertiary amine, that is R3N. This tertiary amine accept one proton, and those which accept proton, they are known as weak base. So local anesthetics are weak base, they can accept proton, and which portion accept, this is the tertiary amine, R3N. After acceptance of proton, it becomes R3NH+. So this is how our local anesthetic behaves like weak base. They accept one proton, and which part accept a proton is the tertiary amine. This is intermediate chain, and this is aromatic ring. So most of the drugs, they are either weak acid or weak base. But in pharmacology, some drugs, strong acid, strong base. And there are one more category which may be very weak acid and very weak base. So these are some of the drugs. If you look at these strong acid or strong base, they remain ionized. They remain ionized at all pH levels, whatever the pH. But if you look at these very weak acid or weak base, they remain unionized at all pH values. So these are the two categories where most of the drugs are either weak acid or weak base. There are some drugs which may be strong acid, strong base, and either very weak acid, very weak base. Weak acid donate proton, weak base accept proton, and these remains ionized and these remain unionized at all pH values. So if I summarize all these at one place, then this is the point where we have weak, at here we have very weak, and at this place we have strong. Very weak acid or very weak base. These are weak acid or weak base, and these are strong acid or strong base. This intermediate category is the most common category. So most of the drug lies here in this portion. Very weak and strong. These are some of the drugs. These strong acid or base, they remain ionized at all different pH, and these very weak remain unionized. So we'll discuss this portion where most of the drug lie in the category of weak. So most of the drugs are weak, either weak acid or weak base. And in here they are very weak, either weak acid or very weak base. And in this category we have some strong acid and strong base. So these very weak acid or very weak base, they remain 100% unionized at all pH values. And this category of drug 100% ionized at all pH values. But these weak acid or weak base, these are the drugs which follows your pH partition hypothesis, or they follow Henderson-Hasselbalch equation. They follow this equation. What the equation says, weak acid and weak base pK plus log unionized divided by ionized, means this is the category of 100% ionized and this is the category of 100% ionized, unionized. But these drugs, they lies between, for example, ionized and unionized. They may be 99%, 1%. They may be 86%, 76%, 14 and 24. Or they may be 50%, 50% ionized and unionized. But in this category, where most of the drug are weak acid or weak base, they are not 100% ionized or ionized, means that percentage varies within the limit of 100%. For example, they can be 50-50. They can be 99:1%. So this is the percentage. These weak acid or weak base, they ionize in percentage. And these different percentage depends upon number 1 pH of the medium, number 2 pKa of the drug. pH of the medium and pKa of individual drugs. So what is the percentage? What is the percentage? This percentage depend on the pH and pKa. pH and pKa. This side 100% unionized, and this side we have 100% ionized drugs. 100%. And most of the drugs, they fall in this category. That is, they are either weak acid or weak base. So these are weak acid or weak base. They follow this equation. And with the help of this equation, we can calculate what percent is ionized and what percent is unionized. So if we apply this equation to weak acid, so remember weak acid, pH equal to pKa plus log A divided by B. For acid, this A should be numerator. And for weak bases, pH equal to pKa plus log, this B should be numerator. So you can easily remember A should be on the top. Here for weak base, B should be on the top. So these are the two equations, one for weak acid and one is for weak bases. So our topic for today's topic is related with this portion, that is weak bases, which follow this equation. And what weak bases we are discussing, they are the local anesthetics like lignocaine, bupivacaine, and their structure is aromatic ring, intermediate chain, and tertiary amine. This portion, tertiary amine portion, it accept a proton. So why they are known as weak base? Because they accept proton. And which part of their structure accept a proton is the tertiary amine part, accept a proton. They are known as weak base. So from this equation of weak bases, we'll discuss all the parts which are written one by one. First, we'll see what are these B and A. What is the meaning of B and what is the meaning of A? So B you can remember with the mnemonic bulls, that is base form, unionized form, unprotonated form, and lipid soluble form of the drug. A means you can remember the opposite, acid form, ionized form, protonated form, and water soluble form. So these two are the unionized and ionized, which is normally written in books. So you can remember from B by A. This B, what is the meaning of B in terms of its function? This B form, it helps to cross cell membrane, whether of neuron or other. Once it crosses the cell membrane, slow or faster, this B form determines onset of action. Means slow onset, and some drugs have rapid onset. So this is the function of the B form, unionized form. It crosses the cell membrane and determine the onset of the action. That is slow onset or rapid onset. And this B form is determined by the difference of pH minus pKa. So pH minus pK difference determine the B form. B form cross the cell membrane, that is onset of action, whether it is slow onset or it is rapid onset. They are related with the B form. And B form is less or more, that is determined by the difference of pH and pK. And this A form, which is nothing but the ionized form, it determines duration of action. It determines duration of action. How long, for example, this is the neuron, and this is the sodium channel, and this is the ionized form. If ionized form is more, A form is more, the more will attach to the sodium channels, and that will increase duration of action of your local anesthetic drug. So this B will determine speed of onset, slow or rapid speed. A determine duration of action. If A is more inside the neuron, duration will be more. And who determines B and A? So this is the again difference of pH minus pKa. That we'll discuss later. So we discussed the meaning of A and B. This A and B, they remain in equilibrium. B ionized form, A ionized form, they remain in equilibrium. Means their percentage keeps on changing. Then who determines this percentage? This percentage is determined with the help of pH, number 2, pKa. pH and pKa. So in this equation, B and A we discussed. Now we'll see what is pKa and what is pH. So as we discussed, for very weak acid, very strong acid, 100% ionize at all pH values. And this 100% ionized again at all pH values. But here we have different pH values. We have different pH values. For example, This is your 2% lignocaine vial. The pH here is 6 in this vial. This is the animal whose tissue fluid, blood, extracellular fluid pH is 7.4 and intracellular pH is 7.1. So we have three different pH values. Suppose from this vial you want to inject lignocaine to this animal, want to infiltrate the lignocaine, then outside the neuron you will find pH 7.4. And once you enter the neuron, it is 7.1. So we have three different pH values. Again, in some tissues, in case of abscess, in case of inflammation, any kind of infection, infected tissue, pH will be acidic. If there is fetal acidosis, again the pH will be acidic. So we have different pH values, and at different pH values the percentage is different. We'll discuss the percentage as these three values. Then pKa. pKa is nothing but it is the pH at which 50% of the drug is ionized and remaining 50% is unionized. This is the pKa. Again, pKa is constant for a drug. It is constant. For example, for lidocaine or lignocaine, it is 7.9. For bupivacaine, it is 8.1. Chlorprocaine, 9.1. So for different drug, its value is constant different. But sometimes it may varies, and it varies with temperature. For example, if you warm a lignocaine vial or if you cool lignocaine vial, so warming or cooling also affect the pKa. Then this pKa correlate itself with speed of onset. Speed of onset. Speed of onset means pKa is inversely to speed. Lignocaine is having low pKa, it is having rapid onset. Bupivacaine is low pKa, so it will be having slow onset. Speed of onset. So that is the relation between pKa and speed of onset. So pH and pKa. weak bases, again pH equal to pKa log B divided by A. So we discussed 3 pH value and 1 pKa. pKa was 7.9, and in the lignocaine vial tissue fluid and intracellular fluid, the pH was different, 6, 7.1, 7.4. So these are the three different pH values and pKa is constant, that is 7.1. What is the relation between this pH and pKa? First we'll see this equation, what this equation explain. So this equation explain the percentage of these two, and this percentage depend on pH and pKa. For example, at this pH, ionized form is 99%, unionized form is 1%. At this place, it is 86:14, and here it is 76:24. So the percentage, they are different according to the pH. So what is the relation between these three pH, that is 6, 7.1, 7.4? There are suppose there are three dogs, A, B and C. Out of these three, this is very further away from the 7.9. The distance is large. So A will reach slowly because the distance is large. But this dog C will reach faster because the distance is very small. It means if the pH, that is 7.4, if the pH is closer to pKa, if we are closer to pKa, onset will be rapid, that is rapid onset. If we are away from the pKa, if the distance is more, if we are away from pKa, onset will be slow. So this is the conclusion from different pH values and their relation with pKa. The distance is more or the difference is more, uh, onset will be slower. And this A and this is C. Difference between pH and pKa is less. So it will reach the distance, the target very faster. Onset will be rapid. Onset will be rapid. The same thing we'll discuss from Henderson equation. We can rearrange this like this: pH minus pKa equal to log B divided by A. So this difference, as we discussed on the scale, this was the pKa and these three are pH, 6, 7.1, 7.4. So the pH and pKa difference Number 1. If this difference is a negative number, the meaning of this is pH is less than pKa. And in most of the cases in most local anesthetic, pH is less than pKa, means their pKa is always higher. If we take an example, lignocaine, pH in the vial is 6, extracellular fluid 7.4, and intracellular fluid 1, extracellular is 7.4, lignocaine pKa that is 7.9, bupivacaine 8.1, and chloroprocaine 9.1. This is the pH of physiological pH, blood pH, tissue pH. All or most of the local anesthetic which are used clinically, their pK value is more than 7.4. Their pK value is more than 7.4. So the first category where pH minus pK, this difference is negative, means pH is less than pKa. That is the case with most of the local anesthetic. So what is the meaning of this negative number? If we take 6 and this lignocaine 7.9 and make 6 minus 7.9, this will be minus 1.9, and this is minus 0.8, and this is minus 0.5. So in all these three, it is a negative number, and these pH, they are less than pKa 7.9. These all are negative. So for example, this is negative 1.9 equal to log B divided by A. So when this pH is less than pKa, number is negative. It means this negative number means this B is less in number. So we have B less. So it will cross cell membrane less and the speed will be less. The slow speed of onset. Slower the speed of onset. Again, we rearrange this log B divided by A. There are two scenarios. This difference is negative or this difference is positive. Most local anesthetic follow this one, and this the difference is positive. It means pK is more than pH, and negative means pH is less than pK. This positive means B will be more B form, more will cross cell membrane, and rapid will be the onset. So what is the example for this? If you combine local anesthetic with bicarbonate, local anesthetic plus additive agent bicarbonate, your result will be rapid onset of action. Why? Because The difference of this pH pK becomes positive and more unionized form is available, more will cross and rapid will be the onset. But in this case, negative number equal to this log B divided by A. Negative means B will be less unionized form, less will cross cell membrane and slow will be the onset. Example, lignocaine. So we started with most of the drugs are either weak acid, weak base. Weak base B by A means B will be on the top. So this is the equation pH equal to pK plus log B by A. These forms B and A, they occur in percentage. And who determine the percentage? pH and pKa. pH may vary. There are different values of pH and pK is constant and B and A unionized or ionized form. The difference of these two will determine that B form is available in high concentration or low. If this difference is positive, you have more B form, rapid onset. Most of the local anesthetic, whether lignocaine, bupivacaine, chlorprocaine, they follow this portion, negative. Means they have less B form, slow onset. So we'll continue what most local anesthetic have. So most local anesthetic pH is less than pKa. For example, physiological pH, tissue, blood or physiological pH is 7.4. 7.4. pKa will take different pKa value like lignocaine pKa 7.9, bupivacaine 8.1 pKa and chlorprocaine, that is pKa 9.1. So their pK value, what is conclusion is here the pH is less than pKa for most local anesthetic drug, and this is the proof of this line. So if we compare this pKa with this, we can take the distance between them. Distance. This distance is large from tissue pH to bupivacaine. They have large difference. This is large difference, means slow onset. And lignocaine, this gap, this distance is less. They have less difference, means rapid onset. So low pKa, that is low distance between physiological pH and this, the difference is less. This is rapid onset case. pK is higher, it means the gap is more, it will reach here slowly, slow onset. So out of these two drugs, lignocaine is having rapid onset, bupivacaine is slow onset. If we talk in terms of this difference, then the reason for slow onset is it is having less B form, unionized form is less, and it is having more B form, that is unionized form is more. So we discussed this pK correlate with onset of action. So this onset of action is mainly determined by pH and pKa. These are the main factors. But there is one more, that is concentration of the drug itself. This is the concentration of drug. We'll take one example. This is the physiological pH 7.4 and we have lignocaine and we have chlorprocaine having pKa 7.9, pKa 9.1. If we take 2% lignocaine and 2% chlorprocaine and compare these two, from this point the distance is less. This distance is less. It will reach the target rapidly. So it is having rapid onset. And if the pKa is here high pKa, this distance is more. It will take more time. That is slow onset. But my question is, can we increase onset speed of chlorprocaine? Answer is yes. If we increase the concentration, make it high concentration, that is, instead of 2% chlorprocaine, if we use 3% chlorprocaine, if we use 3%, then more molecules will be available to diffuse into the nerve and rapid will be the onset. Rapid will be the onset. So if they both have same concentration, then low pKa rapid onset, high pKa slow onset. And if we increase the concentration from 2 to 3%, more molecules will be available, they diffuse into nerve and onset will be rapid. So this chlorprocaine is the exception where it is having high pK value, but still have rapid onset. And the reason for this is high concentration. So this concentration of drug also affect onset of the action. So at the end, we'll conclude our lecture. Most of the drug weak acid or weak base, and we discussed about local anesthetics. Local anesthetics, yes, in their structure they have something tertiary amine group which accept a proton, therefore they behave like a weak base. We'll take one example that is most commonly used, lignocaine HCl. This lignocaine, while it is 30 ml and 2%. This is lignocaine is weak base, very less soluble in water. So this is added as acid is added, and this salt now more soluble, become more stable, and the pH of this vial you purchase from the market, pH is 6. It is acidic. Why it is acidic? HCl is added. Why HCl is added? To make the salt more soluble, more stable. Why to make more soluble? Because lignocaine weak base is very less soluble in water. So the pH is 6. We'll take this in the syringe. Again, the lignocaine pH here is the 6. Then infiltrate to the animal body. Will infiltrate here. Once you infiltrate in the tissues, then outside the neuron, pH is 7.4. Inside, pH is 7.1. Inside the neuron. So we have 3 pH, while extracellular pH outside the neuron, that is extracellular fluid, and 1 pH inside the neuron. And here we have sodium channel, and inside this is the target of your local anesthetic. So target is on the inner side. So from the vial itself to the target of the sodium channel, we encounter three types of pH. Three types of pH. Once you inject outside the nerve, here ionized form is 86%, unionized is 24%. This 24% will help the drug to cross the cell membrane and reach inside the pH of 7.1. At the pH of 7.1, again the equilibrium of this A and B again shifted because of change in pH. Here the ionized form is, it was 76, form is 86 and ionized is 14%. So this 86% ionized form, this form is responsible to bind with the sodium channel. So this ionized form bind with the sodium channel. So at the beginning we discussed about B and A. B to cross the membrane, A to bind with the sodium channel. B determine the speed of onset, that is slow or rapid onset, and A determine duration of action. More the A form, more it will occupy the sodium channel, longer will be the duration of action. So this is the role of A and B, and their percentage again determined by two things, pH and pKa. So from this we reach to the target sodium channel. So in next lecture we'll study structure of this sodium channel, How many states of sodium channel? Then mechanism of action of local anesthetic. So what we discussed today's lecture, most drugs either weak acid or weak base. For weak base, the equation is pH equal to pKa log B on the top, then A. Then we discussed A and B, they are in equilibrium. Their percentage changes according to pH and pKa. And this difference pH minus pKa equal to log B divided by A. This difference either negative or positive. But for local anesthetics, this is negative. Means pH is less than pKa. This difference determines B form is less, or here B form is more. So this is the B form which is related with cell membrane corrosion. And we discussed three pH values, 2, 3, and different pKa values like lignocaine 7.9, 8.1 bupivacaine, and pH for tissue fluid 7.4, intracellular fluid 7.1, pH while it is 6. So we have different pH values, that is one thing, and we have different pKa values varies according to the drug. So these pH values and these pKa values, pK, if it is low pKa, then more will be B form, more will be rapid, that will be the onset. High pKa, less B form, slow onset. So pK is inversely to speed. Sometimes you find abscess, inflamed tissue. In those cases, pH is very low. Means pH is very less than pKa. Because of this, B form is very less and A form is very high. A form means that is charged ionized form. Ionized form. In that case, what happen is ion trapping occur. Ion trapping. So when the ion trapping takes place, when there is pH is very low, for example, this is the maternal and this is the fetus. Fetus pH is 2, 3, 4. That is because of fetal hypoxia, that is fetal acidosis. From the maternal side, if lignocaine or any, it reaches here, it will be ionized. Ionized, more A form. Ionized form. That is called ion trapping in the case of placental transfer. So this is the placenta where lignocaine transfer to fetus, but the acidic pH make more A form charge or ionic form and ion get trapped there. So this is ion trapping.